Find the stationary distribution of the Markov chains with these two transition matrices. So before we get started here, I just want to label a couple things. Let's call this first matrix PA, and then let's call this second matrix PB. Anyway, so for part A, we want to find the stationary distribution, right? So sometimes this could be asked something like, what does this Markov chain converge to? But typically it's said to be a stationary distribution, and all we're trying to find out here is what does this Markov chain do in the long run? And the way this is typically denoted in stochastic processes books or Markov chain books is with pi times our p equals pi, where pi is a vector that can match up to our matrix so we can multiply it nicely, right? So in our case, we're going to have the vector x, y, z because our matrix is a 3 by 3, right? And then this multiplying this vector by itself should lead to itself, right? If it's going to be something that converges, it's essentially what the definition is loosely. So getting right to it here, I'll do this in green. In our case for part A, we want pi times PA equals pi, which is essentially just our vector times our matrix. And then all we have to do is solve a system of linear equations, which is pretty straightforward. I'm not going to solve this system of linear equations here, just because it takes a lot of time, and if you don't know how to do it, you should, and there's a lot of good YouTube videos. If you do, that's good. So I'd say pause the video here if you don't understand how to multiply vectors by matrices or do matrix multiplication, and go and look that up. If not, I'm going to continue, and then all we have to do is solve a system of linear equations. So in our case, we have 0.5x plus 0.2y plus 0.1z should equal x. 0.4x plus 0.5y plus 0.3z equals y. And then we have 0.1x plus 0.3y plus 0.6z equals z. Now, if you brushed up on your linear algebra, you're going to see that these three statements are linearly dependent, which isn't going to work. We're not going to be able to solve for x, y, and z. So what happens there, you can put this in a system of equations solver on your calculator or online. Doesn't really matter how you get it done. You could also do it by hand. I'm not going to do it here, but what we do need to note is that this is also a probability vector, right? So x plus y plus z has to also equal 1. So when you're solving for this, we could take any one of these equations out and then just use these equations instead of the three we originally had to solve for that. So once we solve for this, I'll call this pi a because it's for part A. Pi a comes out to be 11 over 47 for our x variable, 19 over 47 for our y, and then since it has to add to 1, this has to be 17, right? Over 47. So that's our answer for part A. I'll underline that in red. And that's essentially how you're going to solve that every single time. If you're given a transition matrix P, like we were given, we're just going to use this formula, pi times P equals pi, solve the system of linear equations, and it will give you the stationary distribution, or what this Markov chain converges to, which is what we want. So for part B, we've got a few definitions because this happens to be doubly stochastic. So I have enough time here to solve this on this video, so I'm going to continue to. But first we just need to go over what exactly a doubly stochastic Markov chain is. Now we know a transition matrix is said to be doubly stochastic if its columns sum to 1. So mathematically, right, the summation over all x of the probability of going from x to y equals 1. So essentially what we're trying to do here is all of the rows as well as columns add up to 1. So typically in a transition matrix, you can see in part A, say for this first row here, we've got point A plus, or excuse me, 0.5 plus 0.4 plus 0.1 equals 1, right? So this is what makes this a transition matrix. But what makes part B a doubly stochastic transition matrix is that our rows also sum to 1, and you can verify this in our picture. I'm not going to insult anyone's intelligence. I understand, everybody knows that 5 plus 3 plus 2 equals 1, 4 plus 2 equals 1, and so on and so forth. And you could also note that the rows also sum to 1. So this makes this doubly stochastic. So since our part B is doubly stochastic and we have 3 states, we can then move on to a theorem that states if P is a doubly stochastic transition probability with n states, then the uniform distribution is a stationary distribution, such that our stationary distribution is just 1 over n. So, like I said, above we have a matrix that's doubly stochastic, all of its rows and all of its columns sum to 1. So then we can use this statement here to state for B, I'll note it as pi B, just equals 1 over n. And we've already said that we have 3 states in our chain, so this is just 1 over 3. And that's our answer for part B. Pretty clear cut whenever you see a matrix like that, or whenever you get asked a question about given a transition matrix, you should check to see if it's doubly stochastic, and then you can use this theorem where the convergence or the stationary distribution of a doubly stochastic chain is just 1 over n for all cases. So that's pretty straightforward.